Hello everyone, welcome to Digital Communication Tutorials. In this video, I'm going to show you how to find an expression for the average probability of error for a binary PCM system. Let us start by considering a binary encoded PCM wave represented by S of t that uses the non-return to zero unipolar or on-off format. The moment I say binary encoded PCM wave, you should understand the PCM code words are only represented in terms of two symbols which are 0 and 1. So, when symbol 1 is sent, the input signal S of t equals S1 of t, which is defined as S1 of t equals square root of E max divided by TB over the interval 0 to TB, where TB is the bit duration and Emax is the maximum or peak signal energy. Please note, since we have considered a binary encoded PCM wave, when symbol 1 is sent, we are actually sending a pulse of certain amplitude and duration TB. On the other hand, when symbol 0 is sent, we should note we are considering an on-off format. So, the transmitter is switched off for a duration of TB and let S of t equal S2 of t when symbol 0 is sent. So, S2 of t can now be represented as 0 over the interval 0 to TB. Moving on, let us now consider the channel noise W of t to be modeled as an additive white Gaussian noise, simply AWGN, with 0 mean and a power spectral density of N0 by 2. Correspondingly, the received signal now equals X of t equals signal part S of t plus the noise part W of t. So, as you can see, S of t is the transmitted PCM wave that will either be equal to S1 of t or S2 of t, depending upon whether symbol 1 or symbol 0 was sent, and W of t is the noise component. We know that for an AWGN channel, the optimum receiver is either a matched filter or a correlator. Here, for our derivation, we will be assuming a matched filter as shown in the diagram 1 here. You should see we have the input signal S of t and the noise component W of t, which are fed to the matched filter. The X of t is the received part at the output of the channel, which is then fed to the matched filter. The output of the matched filter is sampled at t is equals to TB to create a sample X1, which is then fed to the decision device. Now, depending upon whether the X1 is greater than or less than the threshold, a corresponding decision will be made and that will be given as the output. If in case X1 equals the value of the threshold, then the decision is made by flipping a fair coin. That is how the matched filter works. I already have created a video on matched filter. I would request you to kindly refer to that video for more information as to how the matched filter works. Let us now move on and find the probability of error incurred by this receiver using the signal space approach. By analyzing equation 1 as well as equation 2, we recognize that the binary PCM system has only one basis function. The basis function is identified by taking the common terms in the equations 1 and 2. Here you see the S1 of t signal has an energy of root of Emax, whereas S2 of t has an energy equals to 0. So I can write S2 of t as energy multiplied by 1 by root TB. So 1 by root TB is common in both S1 of t and S2 of t, and that in fact will become the basis function. That is what is shown here. So the basis function is given by phi1 of t equals to root of 1 by TB over the interval 0 to TB. By using the basis function, we can now express the transmitted signals S1 of t and S2 of t as S1 of t is equals to square root of Emax multiplied by phi1 of t over the interval 0 to TB. Similarly, S2 of t is equals to 0 into phi1 of t, once again over the interval 0 to TB. So, by recognizing that there is only one basis function required to represent both S1 of t and S2 of t, we can state that the binary PCM system is characterized by having a signal space that is one-dimensional in nature with two signal points, and the coordinates of these two signal points can be derived by using the equations here. That is, the first signal point which represents S1 of t is represented by S11, which is equals to integral 0 to TB S1 of t into phi1 of t dt, which will equate to root of Emax. On the other hand, the second coordinate, which is represented by S21, can be calculated as integral 0 to TB S2 of t into phi1 of t dt. Since S2 of t is 0, the complete integral reduces to 0. Now we have 2 points which can now be plotted on the signal space, and this is what is shown in the diagram here. So the message point corresponding to S1 of t or symbol 1 is located at S11, which is equal to root of Emax. And the message point corresponding to S2 of t or symbol 0 is located at 0. We assume that the binary symbols 0 and 1 at the input occur with equal probability. This is a very important assumption because this is going to help us a lot in deriving the probability of error for both symbol 0 as well as 1. So let us start by assuming the binary symbols 0 and 1 occur with equal probability. Correspondingly, the threshold used by the decision device has to be halfway point between the two message points, which is equal to root of Emax divided by 2 here. So now we draw an imaginary plane that forms the decision boundary for this constellation or signal space. To realize the decision rule as to whether symbol 1 or symbol 0 was sent, we partition the one-dimensional signal space as shown in the diagram here that creates two decision regions. The first decision region is a set of points that are closest to the message point at root Emax, and the second decision region is once again a set of points closest to the second message point at 0. Let the corresponding decision regions be represented as Z1 and Z2 respectively. The decision rule is now simply to guess symbol 1 or S1 of t was transmitted if the received signal point falls in region Z1. On the other hand, we will guess symbol 0 or signal S2 of t was transmitted if the received signal point falls in region Z2. That will be our decision rule. In doing so, two kinds of erroneous decisions are likely to be made by the receiver. The first one is actually called as the first kind of error, where symbol 0 is sent, but the channel noise W of t is such that the received signal point falls inside region Z1, and so the receiver decides in favor of symbol 1. This is called as error of first kind. On the other hand, we have the error of second kind, where symbol 1 is transmitted, but the channel noise W of t is such that the received signal point falls inside region Z2, and so the receiver decides in favor of symbol 0. So we have two types of errors. We actually name them as two kinds of errors. The first kind is symbol 0 transmitted, but decision is made in favor of symbol 1. On the contrary, the second kind of error is symbol 1 is transmitted, but the decision is made in favor of symbol 0. So we have two types of errors, and we call these conditional errors as errors of first kind and second kind respectively. As you can see in the matched filter diagram here, the received signal point is calculated by sampling the matched filter output at time t is equals to tb. This creates a number x1, and you can express this x1 in terms of equation as x1 equals integral 0 to tb x of t into phi 1 of t dt. We should note that when symbol 0 is sent, the mean of x1 is 0. On the other hand, when symbol 1 is sent, the mean of x1 is root of Emax. However, regardless of which of the two input symbols were sent, the variance of x1 is always equal to n0 by 2, where n0 by 2 is the power spectral density of the channel noise. This concept is taken from our previous discussion by the title Response of Correlators for a Noisy Input. Let us now move on and calculate the probability of making an error of first kind, which is assuming the symbol 0 is transmitted. Under this condition, an error is made if the receiver decides in favor of symbol 1. Now, let us go back to the signal space diagram and analyze the decision region that is associated with symbol 1. You can see the region Z1 is marked by the starting point, which is equals to root of Emax by 2, and the ending point is infinity. So the decision region that is Z1 is represented by the equation Z1 given by root of Emax by 2 till infinity. So if x1 has a value anywhere between root of Emax by 2 and infinity, then a decision is made always in favor of symbol 1. That is what it means. Now currently you should note we have transmitted symbol 0. However, the decision is made in favor of symbol 1. Moving on, since the random variable x1 with a sample value of small x1 as defined in the previous equation as a Gaussian distribution with zero mean and a variance of n0 by 2, the likelihood function under the assumption that symbol 0 was transmitted is given by, this is a Gaussian equation, we represent the likelihood as fx1 of x1 given 0 equals to 1 divided by square root of 2 pi into variance of x1 multiplied by exponential of minus 1 divided by 2 into variance of x1 multiplied by the signal, which is x1 minus its mean square. This is the Gaussian equation. Now let us substitute wherever variance of x1 is there by n0 by 2, and since we have transmitted symbol 0, the mean of x1 is supposed to be 0. That is what we have previously stated. So I will now represent variance of x1 as n0 by 2, both here as well as here, and I am going to represent mean of x1 as 0. Please remember, symbol 0 is transmitted and therefore the mean value is 0. Let us simplify this to get the final expression as 1 divided by square root of pi into n0 into exponential of minus x1 square divided by n0. This likelihood function is plotted in the figure 2 here. Now let us assume Pe of 0 denotes the conditional probability of deciding in favor of symbol 1 when symbol 0 was transmitted. That is, Pe of 0 is the probability of error of the first kind. Now the probability of error Pe of 0 is the total area under the shaded part of the curve which lies above root of Emax by 2. Let me go back and show you that. Now you can see here we have currently plotted the likelihood function when symbol 0 was transmitted. So the shaded part of the curve which lies above root Emax by 2 is what is actually Pe of 0. Therefore, to get Pe of 0 expression, all we need to now do is to simply integrate fx1 of x1 given 0 over the interval root Emax by 2 till infinity. That is what we have shown here. So you can see Pe of 0 equals integral root of Emax by 2 till infinity, the likelihood function multiplied by dx1. Let me now substitute for fx1 of x1 given 0 from the previous expression, and I am taking this 1 by square root of pi into n0 towards the constant term. So what remains is integral root Emax by 2 till infinity exponential of minus x1 square by n0 into dx1. Let us now change the variable and let the new variable z be a part which is, except for the negative symbol, the square root of the exponential term. I repeat, the square root of contents of the exponential term except for the negative symbol will be the new variable. So z is equals to x1 divided by square root of n0. Now since I have changed the variable from x to z, I need to now find new limits for the integral as well as represent the value of dx1 in terms of dz. To do that, now I am going to substitute the old integrals in place of x1 and find new integrals for z. That is, when x1 is infinity, z is equals to infinity by square root of n0, which anyhow is once again infinity. On the other hand, when x1 is square root of Emax by 2, z is equals to square root of Emax divided by root n0 multiplied by 1 by 2. That is what is given here. So it's 1 by 2 into root of Emax by n0. Lastly, to find dx1, I simply have to differentiate this equation. So dz divided by dx1 is equals to 1 divided by square root of n0. So therefore dx1 is equals to square root of n0 multiplied by dz. Now let us substitute all these values back into the equation 13 and write a new expression for Pe of 0, which is given by 1 by square root of pi into n0 into the integral. The lower limit is now 1 by 2 into root of Emax by n0, which we found here. The upper limit is anyhow infinity, so it is replaced as it is, into exponential of minus z square into dx1 is written as dz into root of n0, which we found here. So this is our new expression. Here you can see we have 1 by square root of n0 and then we have square root of n0 in the numerator. So let us cancel them out to get a new expression as Pe of 0 equals 1 by square root of pi integral limits as it is exponential of minus z square into dz. Right. So this is where we are supposed to stop while deriving the probability of error equation, because now we don't have to anymore simplify this expression, but rather we will compare it to one of the most important functions in the error probability derivation, which is the complementary error function given in the form ERFC of u equals 2 divided by square root of pi integral u to infinity exponential of minus z square dz. This is called as complementary error function. So all we now need to do is to simply compare PE of 0 expression with respect to ERFC expression and write PE of 0 in terms of ERFC, which by careful observation reduces to PE of 0 equals. Please note we have a 2 here, whereas here we don't. So it will be 1 by 2 into ERFC of the lower limit of the PE of 0 integral. That is what we are supposed to write here. Right. So this is the final expression for the probability of error of the first kind, that is symbol 0 transmitted but the receiver decides in favor of symbol 1. Let us now move on and find the probability of making an error of the second kind. So let us assume symbol 1 is sent. Under this condition, an error is made when the receiver decides in favor of symbol 0. So, once again going back to the constellation diagram or the signal space and identifying the decision region boundaries for symbol 0 this time, we start by the lower limit is minus infinity and the upper limit is square root of E max divided by 2. So, this is actually the boundaries for the decision region Z2. That is what we have represented here. You see, Z2 varies from minus infinity to root of E max divided by 2. So, if the received signal point x1 has a value anywhere between minus infinity to root of E max by 2, then the decision is always made in favor of symbol 0. Now, for this particular case, the Gaussian distributed random variable x1 with sample small x1 will have a mean equal to square root of E max and variance once again the same, which is n naught by 2. So, the corresponding likelihood function fx1 of x1 given 1 is shown in figure C here. Let PE of 1 denote the second conditional probability of error given symbol 1 is sent. That is, PE of 1 is the probability of making an error of the second kind. So, the probability of error PE of 1 is once again equal to the area under the shaded part of the curve in figure C. So, when you come back to the diagram for fx1 of x1 given 1, the shaded portion of this curve is PE of 1. So, we will obtain PE of 1 by integrating this area under the shaded part of the curve to get an expression that is very similar to what we obtained for PE of 0. So, PE of 1 is also equal to 1 by 2 into ERFC of 1 by 2 into square root of E max by n naught. Please note the expressions for PE of 0 as well as PE of 1 are exactly the same, and this confirms that the channel is symmetric in nature. Lastly, we move on to determine the average probability of error in the receiver. Now, to determine this, we note that the two possible kinds of error considered before are mutually exclusive in nature. That is, if the receiver chooses symbol 1, then symbol 0 is excluded from appearing and vice versa. Further, we also note that PE of 0 and PE of 1 are conditional probabilities because we have computed them assuming a certain symbol was transmitted. On the other hand, the other symbol was received. So, this is a conditional probability. To find the average probability of error, we would require the input probabilities for symbol 0 as well as symbol 1. Let P0 represents the a priori input probability of symbol 0 and P1 represents the a priori input probability of transmitting symbol 1. Now, since both the symbols are equiprobable in nature, the value of P0 is equals to value of P1, which should be equal to 1 by 2. So, noting that PE of 0 is equal to PE of 1, the final expression for the average probability of error is reduced to PE equals PE of 0 equals PE of 1. So, we can now finally write an expression for the average probability of error for a binary PCM system as 1 by 2 into ERFC of 1 by 2 into square root of E max by n naught. This is the final expression. Now, the important thing that has emerged from this analysis is that the average probability of error PE at the PCM receiver depends only on the ratio of the peak signal energy to the noise power spectral density measured at the receiver output. In fact, to support this statement, we have shown a graph which actually has probability of error along the y-axis and peak signal to noise density ratio on the x-axis. Please note, this term peak signal to noise density ratio is on the x-axis and PE itself is on the y-axis. Let us assume that we require an average probability of error less than or equal to 10 to the power of minus 6. So clearly there is an error threshold below which the receiver performance may involve significant number of errors and above which the effect of channel noise is practically negligible. By looking into this graph, you can see if I want the average probability of error to be 10 to the power of minus 6, the x-axis point that meets this curve is somewhere around 17 dB. So if I maintain the peak signal to noise density ratio to be 17 dB, then the binary PCM system will almost be void of any errors. In other words, provided that the peak signal energy to noise density ratio, which is Emax by N0, exceeds the error threshold. For the 10 to the power of minus 6 case, it is 17 dB. Then the channel noise has virtually no effect on the receiver performance, which is what in fact precisely the goal of PCM. However, you should note, if this ratio drops below the threshold, there is a sharp increase in the rate at which the errors will occur at the receiver. Right. So that is about the derivation for the average probability of error for a binary PCM system. If you like this video, kindly press that like button and subscribe to my channel for more videos on digital communication. Thank you for watching. Have a good day.